this video, we're talking about how to prove whether or not two triangles are similar by the side-side-side similarity theorem, side-angle-side similarity theorem, or angle-angle similarity theorem. And we've got a couple different examples here. The first one we're going to talk about is this first example. We have two triangles, triangle ABC and triangle DEF, and we're trying to prove whether or not they're similar. Well, first of all, remember that similar triangles are triangles that have three congruent interior angles. So in other words, in this example, we'd be looking for angle A to be congruent to angle D, angle B to be congruent to angle E, and angle C to be congruent to angle F. So we're looking for three sets of congruent interior angles. The triangles don't necessarily have to have the same side lengths. One triangle could be smaller than the other one, and the three interior angles still be the same. Moreover, one of the triangles could be rotated or flipped or skewed in some way off from the other one, and that's okay too. The only thing that matters is that all three interior angles of the triangles are congruent across the two triangles. If that's the case, then the triangles are similar. And there are a few theorems we can use to prove the two triangles are in fact similar. One is this side-side-side theorem, and that's going to be the one that we're going to try to use in this first example, because notice that in both triangles we've been given all three side lengths of both triangles, but we don't have any of the angle measures. So SSS stands for side-side-side, SAS stands for side-angle-side, and AA stands for angle-angle. So we don't have any angle, so we know we're probably not going to be able to use side-angle-side or angle-angle because both of those theorems involve an angle. So that means we're going to try to use this side-side-side theorem. What does the side-side-side theorem say? Well, it says that all three sides of the triangle have to be proportional to all three sides of the other triangle. So in other words, if we take the sides that look similar to us, so we can see the shortest side here in triangle ABC is 1.6. So if we say 1.6, that's going to be similar to the shortest side of this triangle, which has a length of 1. So we want to go ahead and set up a fraction. I just did the smaller value on top. So 1 over 1.6. That's got to be equal to, if I look at the next shortest side in triangle DEF, it's 2.5. In triangle ABC, it's 4. And then if I look at the longest side in triangle DEF, it's 3. And in triangle ABC, it's 4.8. So I want to set up this proportion, this equality, and see if all three of these ratios are equal to one another. The important thing to remember is that you always have to keep the lengths of the sides of one triangle always in the numerator, always in the denominator. So notice that all three side lengths of triangle DEF are in the numerators of these fractions. So we've got triangle DEF here in the numerator, and then the three side lengths of triangle ABC are always in the denominator. So triangle ABC is always in the denominator. So we have DEF, 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 and then in the denominators ABC, ABC, and ABC. So we want to make sure we keep that consistent and that we just take the sides that should look like they're congruent and pair those together in the same fraction. So then when that's the case, let's try to get these decimals out of here. We'll multiply everything by 10 so that we can eliminate the decimals. So this is then going to become 10 instead of 1. This is going to become 16. This will become 25. This will become 40. This becomes 30, and this becomes 48 when we multiply everything through by 10. Of course, we're not changing the value of any of these fractions because when we multiply both the numerator and the denominator by 10, it's just like multiplying by 1, so we're not actually changing the value. So then if we reduce these fractions to their lowest terms, 10 over 16, if we divide both of those by 2, 10 divided by 2 is 5, 16 divided by 2 is 8, so we get a fraction in lowest terms, 5/8. What about 25 divided by 40? Well, if we try to get this fraction in lowest terms, we can divide both the numerator and the denominator by 5. 25 divided by 5 is 5. 40 divided by 5 is 8, so again we get 5/8. What about 30 over 48? Well, trying to get this fraction in lowest terms, we should be able to divide both the numerator and the denominator by 6. 30 divided by 6 is 5, and 48 divided by 6 is 8. So what we can see then is that we end up with three equivalent fractions. In other words, the side lengths are proportional to one another in the same ratios. So when we end up with three fractions equal to one another like this, we can say that by the side-side-side theorem, these two triangles are in fact similar. What about a second example? In this one, we have triangle MNO and we have triangle PQR. We've been given just 2 angles in each triangle, not any side lengths. We're probably not going to use the side theorem or the side angle side theorem because we don't have any side lengths. What about the angle angle theorem? Well, if we look at these 2 triangles, we can see that triangle MNO has angle measures of 45 degrees and 60 degrees, and that triangle PQR has angle measures of 75 degrees and 60 degrees. So they both have a 60-degree angle, but this one has a 45 and this one has a 75. So maybe you'd say that the angle-angle theorem doesn't apply here. Remember that the angle-angle theorem tells us that we're looking for 2 congruent angles to prove that the triangles are similar. So all we need are 2 congruent angles. We already have one. We have a 60-degree angle in both triangles, and we just need a second congruent angle. So the trick here is to remember that the interior angles of a triangle are always going to sum to 180 degrees. So to find this third missing angle here, what we'll do is we'll take 180 degrees and we'll subtract 60 degrees and 45 degrees. What we end up with then is 180 minus 60 is 120, so 120 minus 45. 120 minus 45 is going to be 75, so we end up then with 75 degrees. And we don't even have to find the missing angle, angle P here, because what we can see is that we have a 75 and a 60-degree angle in MNO. We also have a 75 and a 60-degree angle in PQR. Therefore, because we have 2 congruent angles, then the angle-angle theorem proves that these 2 triangles are similar. And remember, similar triangles, they may have different side lengths, but they have 3 congruent interior angle measures. If we were to find the missing angle measure in PQR, of course we would end up with 45 degrees, and we would be able to use any 2 angles in the triangle to prove by the angle-angle theorem that these 2 triangles are similar. In our last example here, we have triangle STU and triangle XYZ, and we want to try to prove that they are similar. Clearly, we can see that the side lengths are different, but of course they might still be similar. So in both triangles, we've been given information about 2 sides and an angle. So we're probably going to try to use the side angle side theorem to prove that they are in fact similar. What we know is that these 2 sides, side SU and side TU, that they are congruent. So we could, for example, call this side length X, and if this is side length X, then the length of this side is also X because these 2 sides are congruent. Over here in this triangle, we've been told that these 2 sides are congruent, so if we called this side length Y, we'd also be able to say that this side length was equal to Y because we know that these sides are congruent. So then if we set up a proportion between these 2 triangles, we take this base here, this side SU, and set it up in a ratio with side XZ in the other triangle, and we could say X over Y. We'd want to set that equal to a ratio of the other 2 sides, and again, we'd have X over Y. So in the same way that with this first example, we ended up with 5 over 8 equals 5 over 8 equals 5 over 8, here we've ended up with X over Y equals X over Y. So these 2 side lengths, side SU and TU, are in fact proportional to sides XZ and YZ. Therefore, we've got the side and side part of this theorem covered. And of course, we can see that we have a right angle and a right angle, and it is the included angle between the 2 proportional sides. It has to be the included angle. If we were given information about this angle here or this angle here, the non-included angles, or this angle here or this angle here, these angles are outside the 2 proportional sides. We need the angle that's between the 2 sides we have information about. And in fact, that's the case here. We have the 90-degree angle between the 2 congruent sides and between the 2 congruent sides. So because it's the included angle, we also have this angle, 2 congruent angles between the triangles, this 90-degree angle and this 90-degree angle. Therefore, we can prove by the side angle side theorem that these 2 triangles are similar.